Every year, thousands of new patents are published in the field of chemistry. These documents contain the blueprints of new compounds used in material science, medicine, manufacturing, and many other fields. Although the amount of knowledge stored inside these documents is vast, a lot of important information, such as the chemical structures, are defined within images and chemical drawings. If we want to unlock this information for large-scale chemical analysis and accelerating chemical discovery, we need a reliable way of extracting this information into a structured format. MarkushGrapher-2 addresses this problem, extracting complex chemical structures from images into string representations called smiles. Our model is able to parse images ranging from standard molecular structures to complex multimodal Markush structures containing variable groups, frequency and variational indicators, as well as descriptive text. To understand how MarkushGrapher-2 works, let's take a closer look at the model architecture. The model takes as input image crops of the chemical structure found within the patent document. The image is fed into two complementary encoding pipelines. Pipeline 1 consists of a vision encoder taken from the model MolScribe, pre-trained for the task of standard molecular recognition. This is followed by an MLP projector. The second pipeline consists of a dedicated module called Chemical OCR. This recognizes and locates the textual content within the input image. Now we are able to jointly encode vision, text, and layout modalities using a mechanism proposed in the foundational document AI model called UDOP. To do this, we concatenate the textual tokens with the vision tokens. To provide additional layout information, we use the center locations of the bounding boxes and align the corresponding vision tokens with their respective OCR text tokens. The obtained embedding is sent through a VTL encoder as proposed by UDOP. Finally, the embeddings of both pipelines are concatenated into a joint representation and sent through a text decoder to predict a string representation called CX smiles. This string captures the molecular structure, variable groups, cycle connections, and repeating groups of the input image. It further predicts a table containing the possible substituents of the variables within the structure. The overall architecture is trained in two phases, designed to adapt the visual features of the pre-trained encoder in pipeline 1, while further augmenting it using the vision, text, and layout encoding of pipeline 2. Using the given setup, we are able to achieve competitive performance on molecular recognition, as well as substantially outperforming state-of-the-art models for multimodal Markush recognition.